Welcome to lecture 13. My name is Professor J. N. Mandal, Department of Civil Engineering, Indian Institute of Technology, Bombay, Mumbai, India. The name of the course Geosynthetics Engineering in Theory and Practice. This is module number 3, lecture number 13, Geosynthetics properties and test methods. Recap of the previous lecture: we have completed pull out or anchorage resistance, tensile behavior of geomembrane, tear resistance of geomembrane, seam in shear and seam in peel test, and then we are continuing hydraulic properties, that is porosity, AOS apparent opening size and POA percentage opening size. So, next we will address the permittivity or cross plane permeability as per ASTM D4491 and ISO 11058. This test is very important in hydraulic related structure. So, here you can see that this is the geosynthetics material and water flow into the geotextile material and water out from the geotextile material. So, this is the flow Q in and this is the flow Q out, and this is the thickness of the geotextile material is Tg. So, when the water or liquid passes across the geosynthetic material is called permittivity. The main function of geosynthetics is the filtration when the water flow perpendicular to the geosynthetic material. Now, that what are the theory? From the Darcy's equation we know Q is equal to K into N into I into Ag, Kn, and I is delta H by Tg. Tg is the thickness of the geosynthetic material and delta H is equal to head loss, and Ag is equal to area of geosynthetics, and area of geosynthetics is length into width. You can say this is the length of the geotextile material and this is the width of the geotextile material. So, area will be length into width. So, we can write this Ag also length into width. So, from this equation we can write Kn by Tg, this is Tg, is equal to Kn by Tg is equal to Q by delta H into Ag, that means Q by delta H into Ag. So, this Kn by Tg which you call the permittivity or which is designated as a psi. So, psi is equal to Kn by Tg is equal to Q by delta H into Ag, and unit of the permeability is per second and flow rate is meter cube per second. Kn N is the hydraulic conductivity normal to the geosynthetics meter per second, Ag area of geosynthetic, that is L into W, length into width of the geosynthetics in meter square, and delta H is equal to head loss in meter, and Tg is the thickness of the geosynthetic material in meter. Now, you can also draw a correlation between the flow rate per unit time, that is Q by Ag, to the delta H. That means this is Q by Ag to delta H. So, if you can draw the relationship between the flow rate per unit area to the delta H, and you can draw this tangent and this slope, which will give you the value of permittivity. So, at different hydraulic gradient, the flow rate Q will be different. The slope of Q by Ag versus the delta H curve at the origin give the permittivity. So, there are other methods also you can determine the permeability test. One is constant head test, another is following head test. So, constant head permeability test. So, this is the schematic view of the constant head, and let this what will be the total storage of water at the time, that is delta of T. So, this is the geotextile material and this is the porous, this at the top and the bottom, and this is the reservoir for the water collection, and this is the loading arrangement. This is water is in, and this has a constant water head, and this is the clamp trench where geotextile is tightened, and then ultimately water come out from here. This is the water cylinder and this is the loading pad. So, this is a kind of the loading arrangement, and this is the reservoir of for water collection. So, you can collect the water. So, let the total storage water at the time delta T is equal to Q meter cube. So, flow rate Q can be determined from this equation, small q is equal to capital Q by delta T meter cube per second. Now, that is this equation used to determine the permittivity. Similarly, following head permittivity test. You can see this is the initial time T0 and for the initial height Hi, this is the final time Tf and this is the final height Hf, and this is the stand pipe, water is flowing to the stand pipe and geosynthetic material is here. This red color geosynthetic material is here. So, you know that following head test. So, this following head permeability test also you can determine. From the following head test permeability can be expressed, psi is equal to 2.3 small a by Ag into delta T log of H1 by Hf, and this psi which we call permittivity, this expressed at per second. A is area of the stand pipe meter square. This is the A of this is the stand pipe and this area is small a. So, small a is area of stand pipe. Ag is equal to area of geosynthetics. You know this is the geosynthetic material. You can calculate that what will be the area of geosynthetic material, and then delta of T you know that is Tf minus T0, that is change in time. This is Tf T0. So, change in time, this is what is delta T, and then Hi and H0 initial head at time T0, Hf initial head at time Tt, that is Hi at the time T0, Hf at the time Tf. So, you can calculate this what should be the permittivity of the geosynthetic material by following head permittivity test. So, this test is very important, permittivity test. Similarly, there is another term is very important, that is transmittivity or in plane permeability. This is as per ASTM D4716 and ISO 12958. Here you can see that this is the geosynthetic material, and major function of geosynthetic is the drainage. When the water flow along the plane of the geosynthetic material under some applied load, the test is conducted under a constant head like this. this is geosynthetic material and this is applied load. I will tell you later on, you are applying the load and this is geosynthetic material. That means that here to test is to be conducted under a constant load. Here you can see that this is the length of the geotextile Lg, this is width of the geotextile Wg, this is thickness of the geotextile Tg, and this flow in is Qin and flow out is Q out. So, this water or liquid flow along the plane of the geosynthetic material, that is why it is called transmittivity. So, now again from the Darcy's equation we can derive the expression for transmittivity, that means Q is equal to Kp into I into Ag, or Kp into I into Ag is the area, that means this area will be this area, that means this is the Wg and this is the thickness Tg. So, this area will be Wg into Tg. So, that is why this is Wg into Tg. So, then Kp into Tg will be equal to Q by Wg into I. Okay. So, transmittivity which can be expressed as theta is equal to Kp into Tg is equal to Q by Wg into I. This theta is transmittivity of geosynthetics, and this unit of this transmittivity is meter square per second, and Q is the flow rate meter cube per second, Kp is the hydraulic conductivity in plane geosynthetics meter per second, I is equal to hydraulic gradient, that is delta H by Lg, and delta H is the head loss, and Lg is equal to length of the geosynthetic material, Wg is equal to width of the geosynthetics, and Tg is equal to thickness of the geosynthetics. So, you remember this equation, what is transmittivity, that is theta is equal to Q by Wg into I. So, like permittivity, you can also obtain that flow rate with that is Q by this one, Q by I. So, this related with the hydraulic gradient I. So, different hydraulic gradient flow rate Q will be for different. So, you can see here the slope of Q by Wg versus I curve. So, this will give you the slope, this slope which you call that theta. So, this theta value will give you that transmittivity value. So, this transmittivity also test also can be conducted by full length in plane flow or radial in plane flow. So, you can see full length in plane flow. So, here that sample size may be 200 meter length and this is 100 millimeter width, and this geosynthetic material is placed between the two plates, and on the top and bottom of the geosynthetic there will be an impermeable material, here impermeable material, and then this is the loading system here. You can see these are all assembly for this, for performing the transmittivity test, and this is full length of the plane. That means you can see here schematic diagram, this is a geosynthetic material and this is the base plate, top also some base plate, or it will be the impermeable material, and this loading is applied on the top, this loading is applied on the top, and water is supplied, and this at a constant head from this reservoir, and this water can pass along the plane of the geosynthetic material, and then you are collecting the water in a measuring cylinder. So, water is out from here. So, there will be a head, that is delta of H. So, for a particular load constant load. So, you can measure what will be the quantity of water has been carried out at a particular time, and then you can apply the load. Let us say initially you applied 50 kilopascal, then 100, 250, 350, 450, 550, like that continue, and each and every time you have to give some constant load and measure what will be the quantity of water flow through the geosynthetic material under different loading. So, under different loading you can calculate what will be the quantity of water. So, I am giving one example. Let us say the length of the sample LG is 200 millimeter, width of the sample WG is 100 millimeter, thickness of the sample 0.5 millimeter, flow rate Q is equal to 1 into 10 to the power minus 6 meter cube per second, head loss is 10 centimeter. Determine the transmittivity and in plane coefficient of permeability of the geotextile. So, here is the solution. We know transmittivity theta is equal to Kp into Tg, that is equal to Q by Wg into I. So, Q by Wg is I is delta H by Lg. So, theta is equal to Q is 1 into 10 to the power minus 6, this divided by Wg, and Wg is the width of the sample is 100 millimeter. So, this is in terms of the meter. So, 110 to the power minus 3 into delta H is the head loss is 10 centimeter. So, meter 10 into 10 to the minus 2, this divided by Lg. Lg is the length of the sample 200 millimeter. So, 200 into 10 to the minus 3. So, you can have theta value 2 into 10 to the power minus 5 meter square per second. Now, this you calculate what is the transmittivity, and the unit is meter square per second. Yet also to calculate what will be the coefficient of permeability of the geotextile. Then coefficient of permeability Kp is equal to theta divided by Tg. Tg is the thickness of the geosynthetic material and theta is the transmittivity of the geotextile material. So, transmittivity you find out 2 into 10 to the power minus 5, this divided by Tg, that means thickness of the geosynthetic material is 0.5 millimeter. So, theta divided by 0.5 into 10 to the power minus 3 in terms of meter. So, you can have the Kp is equal to 0.04 meter per second. This is coefficient of permeability of the geosynthetic material. Now, this is another test for transmittivity. This is called the radial in plane flow. So, you can see this equipment, and this geotextile is placed somewhere here, and this there is a hole, I will show you. Then water can just pass through radially through this, that means along the plane of the geosynthetic material, and one side this water is in, another side is water is out at a particular hydraulic gradient, and this is the loading arrangement. So, you have to apply the load. So, you can see here some schematic view. So, here the geosynthetic material is placed, this is the base plate, and there you can see this is the one diameter inner and this is the outer. I can say that this is the inner radius of the geosynthetic sample, and this is inner radius of geosynthetic sample, which is Ri, and this is outer radius of the geosynthetic sample, Ro. So, here it is like a circular. So, geosynthetic material is placed on the top of this, and then load is applied. So, you can see here the load is applied on this, load is applied on this. So, then water is supplied, it maintains constant, and then it passes through this geosynthetic material and passes radially means along the plane of the geosynthetic material. It passes from this and this, and then water is out from here and you are measuring in a cylinder. So, this is the difference of delta of H. So, according to the Darcy's law, you know Q is equal to Kp into I into Ag. So, you know the Q into Kp into del d H by dr 2 pi r Tg from here 2 pi r Tg. So, Q is equal to Kp into Tg into 2 pi r dH by dr. So, this Q is like dr by dr is equal to 2 pi Kp Tg into dH. So, it lies between the inner radius of the geosynthetic sample mean R1 to R0. So, you can write Q of log in R0 by R1. R0 is equal to outer radius of the geosynthetic sample, Ri is equal to inner radius of the geosynthetic sample. This is outer radius, this is inner radius. So, you can write Q into log in R0 by R1 is equal to 2 pi Kp Tg and this is delta of H. So, Kp into Tg is equal to theta is equal to Q by 2 pi delta H ln R0 by Ri. So, if you know that what will be the quantity of water passed through this, if you know delta H, if you know what is the outer radius of geosynthetic sample, inner radius of geosynthetic sample, so you can calculate the transmittivity of the geosynthetic material, that is in meter square per second. Now, as I mentioned that transmittivity of geosynthetic material are to be conducted under different normal stresses. You can see here we have performed some tests under different weight and also under different normal stresses. So, this y axis is the transmittivity into 10 to the power minus 6 meter square per second, and this is all under the normal stress, that is begin in the beginning, then you start with the 50 kilopascal, then you keep on reading what will be the quantity of water flow through, and then you determine transmittivity, then again you increase the load to 100 kilopascal, 150 kilopascal, 200, 250, 300, 350 like so on. And then you can obtain the transmittivity versus normal stress curve is like this. You can see that transmittivity increases with the increase of the mass per unit area. This is weight for 700 gram per meter square. This red one is weight for 675 gram meter square. So, you can observe that how the transmittivity increase with the increase in the mass per unit area, and at the same time transmittivity decreases under high normal pressure as well as arrived at a constant value after approximately 250 kilopascal normal pressure. Beyond this pressure, the yarn becomes dense and too much tight to carry the water. So, you have to design for any flow related problem that what should be the normal stress and what should be the corresponding transmittivity, which you will take into account for the design. So, this is very, very important parameter. We will use this kind of the transmittivity value for the design of the prefabricated vertical band drainage and other related problem. Next is endurance properties. So, here abrasion test or abrasion resistance test as per ASTM D4886 and ISO 13427. So, this is the schematic of abrasion test, and this has a inner diameter of about 60 millimeter and the outer diameter at about 90 millimeter. So, you can see this is 60 millimeter and outer diameter is 90 millimeter, and geotextile specimen is disc shape like this, and the sample is placed on the rubber platform and it is rotated up to 1000 cycle under a fixed abrasion wheel to abrade the geotextile material. After this, you take 2 abraded geotextile specimen are cut and tensile strength test is conducted. Take the average value and also you determine the tensile strength of the non-abraded geotextile material. So, strength retained after abrasion will be equal to the ratio of tensile strength of abraded geotextile and the tensile strength of non-abraded geotextile into 100 into percentage. So, this way you can calculate what will be the strength retained after abrasion. There is a ultraviolet or sunlight degradation test. This is as per ASTM D4355 or ASTM D5208 or ASTM D5970. This is also very important test. You cannot keep open in the sunlight all kind of the geosynthetic material. So, this also very important. This is the devices for ultraviolet degradation, and at least you need the 5 sample are tested for the UV test on both machine and the cross machine direction, and geosynthetics should be kept at the side below the 32 degree centigrade. These specimens are exposed to ultraviolet exposure in a Nexon device at 0, 150, 300 and 500 hour. It consists of 120 minute cycle, light only 90 minute, and then water spray and light 30 minute. So, it is a kind of very long term strain. It continue up to the 500 hour, and firstly tensile strength of the specimen without ultraviolet exposure is determined with both in the machine and the cross machine direction. After the UV test, cut the strip or the Radial strip tensile test are carried out on exposed specimen. It will show the deterioration of the exposed sample. For polypropylene or and polyethylene geogrid, minimum 70% strength should be retained after 500 hour as per ASTM D4355. Whereas for polyester geogrid, minimum 50% strength should be retained after 500 hour as per ASTM D4355. So, depending upon the different types of the geosynthetic material, so you will be knowing what will be the percentage of the strength required for this, and after how many hours you have to continue the strength. Now, gradient ratio or clogging test. This US Army Corps of Engineers gradient ratio, that is CW 02215 and ASTM D5101. Gradient ratio test are conducted on soil having permeability more than about 10 to the power minus 5 meter per second. It is suitable for sandy and silty soil where coefficient of permeability less than equal to 10 to the power minus 7 meter per second. This is the photographic view of the gradient ratio test, and here it is the equipment in which you can measure the gradient ratio test. I am just showing in detail about this port, this portion, and how you can measure the head, though most of the time we go for the determination of flow of water through the sample, but in this case of gradient ratio we are measuring the hydraulic head at the various location in the soil geotextile column, and head difference are then converted to the hydraulic gradient, and that way we calculate the what should be the gradient ratio. So, here you can see this is the geotextile material, this is the soil, and this is the soil geotextile column, and these are the piezometric number. This is 1, then this is 2, this is 3, this is 4, this is 5, and this is 6. At this point 1, 2, 3, 4, 5 and 6, and this distance is Z1 and then Z2. So, this Z1 and Z2 is fixed 25 millimeter and Z2 also 50 millimeter. So, from this piezometer reading, when the water will pass through the soil and to the geotextile, then you can measure that what will be the piezometer. So, you know that what is that P3 and also that P of 4, then you can calculate that H1 is equal to P3 plus P4 divided by 2. Similarly, H2 is equal to P5 plus P6 divided by 2. Okay. So, this is P5 and this is P6. So, you know that what will be the value of H1 and H2, and as I said that Z1 is 25 millimeter, Z2 is 50 millimeter, and that is fixed. So, from this you can calculate what will be the gradient ratio. So, gradient ratio is equal to H1 by Z1 divided by H2 by Z2. So, it is not measuring the flow rate, instead of measuring the flow rate, you are measuring the hydraulic head at the various location in the soil geotextile column, and then you are measuring the head difference, and from this head difference you are calculating the gradient ratio. Now, this gradient ratio is designated as GR is equal to H1 divided by Z1 divided by H2 by Z2, and H1 is the head change in millimeter from the bottom of the geotextile to 25 millimeter of the soil above the geotextile, and Z1 is equal to geotextile thickness, that is millimeter plus 25 millimeter of soil, and H2 is the head change in millimeter from 25 millimeter soil above the geotextile to 50 millimeter soil above the previous 25 millimeter, and Z2 is equal to 50 millimeter of the soil. So, in general this acceptable criteria of the gradient ratio. Now, you know that what is head loss, you can calculate that H1 and H2, and you know the Z1 and Z2, and then you can calculate the what is gradient ratio. Now, if the gradient ratio is less than 1, then it is piping. If the gradient ratio greater than 1, it is a clogging. If the gradient ratio greater than 3, then severe clogging, and if the gradient ratio is equal to 1, then you can say it is a stable. But this gradient ratio value also Cross-up engineer suggested that if the gradient ratio value is greater than 3, then not acceptable that kind of the geotextile material. Next, we will perform hydraulic conductivity ratio or HCR clogging test on soil geotextile system as per ASTM D5567. So, this is for long duration of test. For soil with permeability less than 10 to the power minus 5 meter per second, hydraulic conductivity ratio test are conducted. Here is the equipment for the determination of the hydraulic conductivity, and here is the back pressure system, here is the cell pressure system, here is the volume change indicator, and here is the data logger. So, it is nothing but a triaxial chamber, and you measure that what will be the pore water pressure transducer and flexible wall permeable cell here. So, this HCR test is conducted in the 3 stages. First stage is to saturate the soil sample. The second stage is to carry out the primary consolidation of the sample, and third stage is to initialize the flow through marine clay geotextile system. The test is terminated when the hydraulic conductivity of the system stabilized. Hydraulic conductivity ratio can be defined at KSG by KSGO. KSG hydraulic conductivity of the soil geotextile system at any time, and KSGO initial hydraulic conductivity measured at outside of the permeable phase. So, test method and the procedure are like this. The marine clay geotextile filter system compatibility under effective stress condition was carried out by conducting hydraulic conductivity ratio test as specified by ASTM D5567. The test method require placing of the soil and the geotextile in a flexible wall. Permeameter and the desired effective stress and the hydraulic gradients are controlled in the system. Size of the sample, it will be cylindrical molded marine clay sample of 75 millimeter diameter and 50 millimeter height at water content of 60%. Now, here you can see that schematic diagram of hydraulic conductivity ratio test equipment during permeable test stage. Here you can measure, this is the soil sample, this geotextile material is here, this is the bottom pedestal, and this is the rubber membrane, and porous is on the top, and then the top is the top cap. You can also run the back pressure system, so you can volume change indicator. So, you can volume change also you can measure, and this is the burette, and this is the H, this is the vent valve, this is the short flexible tube, and this is, I say that this is a triaxial chamber, this is the top cap, and this is the cell pressure system and the pore water pressure transducer. So, with this equipment you can measure. So, test carried out in the 3 stages, as I said, that saturation of the soil sample done by increasing the cell and the back pressure gradually till the Skempton B value of 0.98 was achieved at the cell pressure of 227 kilopascal and back pressure of 220 kilopascal. Then secondly, primary consideration of the soil carried out at 50 kilopascal effective stress, the cell pressure was maintained at 250 kilopascal and back pressure as 200 kilopascal. It took about 5 days for the completion of the primary consolidation of soil. And thirdly, permeation of the soil geotextile filter system and carried out at a hydraulic gradient is equal to 10 and soil effective stress is equal to 50 kilopascal till the flow was stabilized. So then hydraulic conductivity ratio and pore volume are calculated from the test. So you know HCR is equal to KSG by KSGO. So where KSG is equal to hydraulic conductivity of the soil geotextile system at any time, and that is Q by A into I, where Q is equal to quantity of water flow for the given time interval T. A is cross sectional area of the soil sample, that is 44.15 centimeter square, and I is equal to hydraulic gradient along the system, that is 10. So we know everything, so we can calculate what is KSG or what is hydraulic conductivity of the soil geotextile system at any time. Now pore volume flow or VPQ. VPQ is defined as the ratio of VQ by VP. VQ is cumulative volume of flow that has passed through the sample at any given time, and VP is the pore volume of soil sample is equal to N into V. So N is equal to the porosity of the soil sample at the end of consolidation test, and V is initial volume of the soil sample, that is 221 centimeter cube per day. So for the marine clay and oven jute geotextile filter have been used. So you can calculate N is equal to EC divided by 1 plus EC. EC is equal to E0 minus 1 plus E0 delta V by V is equal to 1.7. So therefore N is equal to 1.7 divided by 1 plus 1.7 is equal to 0.63. What E0 is equal to initial void ratio of the soil sample, that is 2.11, and EC is the void ratio at the end of consolidation stage, and delta of V is the soil volume change at the end of consolidation stage, that is 28.5 centimeter cube, and V is the initial volume of the soil sample, that is 221 centimeter cube per day. So from this you can calculate what is the N. Let us say for the marine clay and oven jute geotextile filter system. So you can calculate KSGO 3.01 meter per second, VP pore volume of soil sample, that is N into V, and N you have calculated earlier, that is N is equal to 0.63, this N is equal to 0.63, and this V is 221, this is V initial volume of the soil sample 221 centimeter cube. So VP will be equal to 0.63 into 221, that means 139.23, this is approximately 140 centimeter cube per day. Similarly also you can calculate for marine clay and polypropylene filter system, where KSGO is 3.20 meter per second and VP is 142 centimeter cube per day. Here KS0 is initial hydraulic conductivity measured at the outset of the permeation phase of the test. So from this test we have tabulated in this figure. There are two types of the geotextile material have been used, that is marine clay with the oven jute geotextile and marine clay with polypropylene filter system. This is the time, days 1 to 21 days, and this is KSG at any given time 10 to the power minus 9 is 3.01. This is hydraulic conductivity ratio HCR. So HCR in the beginning, this is that you know the ratio, so that is 3.01 by 3.01, that is 1, and next one will be 2.86 divided by 3.01, this is 0.96. Then next again 2.62 divided by 3.01 will give that 0.87. Like that you can calculate that what will be the HCR value, and Vs value is centimeter cube per day, is calculated 140 like that, 150 depend upon days. Then Bpq centimeter cube per day, this is 140 by 141, and then next is 151 by 140, 1.08, then 161 by 140, this is 1.15, 171 by 140, 1.22, like that you can calculate that what is Bpq for the defined value of Bq. And similarly, you can calculate for the marine clay polypropylene geotextile filter system also. Now, from this chart, we will show some variation. What is happening? So, this figure shows that graph of hydraulic conductivity of marine clay and geotextile filter system versus time. I am showing in a larger scale here. This is the graph of hydraulic conductivity here. This is hydraulic conductivity to the minus 9 meter per second, and this is time, days. So, this is for the marine clay geotextile filter system value. There are two marine clay polypropylene filter system, marine clay oven jute filter system. You can see that what will be the nature of the curve. That means what is happening, the hydraulic conductivity with respect to the time. So, both the system reach a stable flow condition. The hydraulic conductivity in the marine clay oven jute filter system reaches stable flow condition after 17 days of the initialization of the flow through the system. You can see that in the case of oven geotextile material, this is almost after 17 days, then it is in equilibrium stage here, then after that it is almost constant. But in case of the marine clay polypropylene system, this filter system reach stable flow condition after 13 days. You can see here that it is after 13 days it is in stable condition. So, it depends upon that what will be the type of the material you are using, what type of the soil, and after how many days it is stabilized. This figure shows the relationship between the hydraulic conductivity ratio, that is HCR, and pore volume flow, that is Vpq. This you can see from 0 to 2, and the hydraulic conductivity ratio from 0 to 1.2. This is hydraulic conductivity ratio against pore volume flow, pore volume flow. So, hydraulic conductivity ratio, pore volume flow for both cases. This is marine clay oven jute filter system, a marine clay polypropylene filter system. So, you can determine what will be the pore volume flow. So, pore volume flow is this Bpq, this is pore volume flow. You can see 1 to 1.7, and in this polypropylene filter system it is 1 to 1.81, and this is the HCR value 0.261, and there HC value 0.2621. So, from this data you can draw this diagram pore volume, because for the different hydraulic conductivity ratio what will be the pore volume flow. So, the reduction of the hydraulic conductivity ratio in the marine clay oven jute geotextile system was 0.25 here for the marine clay, you can see 0.25, and in marine clay polypropylene filter system is 0.28. So, this is the some microscopic image of the oven jute geotextile showing clay at the interface. This is done in sophisticated analytical instrumental facility SAFE in IIT Bombay, and test sample after the test, A is the marine clay and B is the oven jute geotextile material, and C you can see how environmental scanning election. So, what is happening? Just to see their structure and their behavior. So, I am drawing some conclusion that hydraulic conductivity in marine clay open jute filter system reached stable flow condition after 17 days of initialization of flow through the system, whereas marine clay polypropylene filter system reached stable flow condition after 13 days. For the given soil and hydraulic condition, the hydraulic conductivity ratio in marine clay open jute filter system reduced to 0.25 and in marine clay polypropylene filter system by 0.28. Marine clay open jute filter system has filtration compatibility similar to marine clay polypropylene filter system for the given hydraulics and soil condition. Visibly, no significant loss of clay fraction was observed in both the system. So, we have tried with both the system with the natural material and also the polymer material, and we observe the nature of the curve is the similar, and the stabilization also is vary depending upon the time. Also it depends upon what should be the pore of the geotextile material. So, we have shown some variation of the hydraulic conductivity ratio and pore volume ratio. We have also shown that what will be the value of hydraulic conductivity ratio. So, in I just mentioned here that Lutici and the William, they have reported that if the hydraulic conductivity value, you can say it is high, then it is a soil loss, and if the hydraulic conductivity ratio or HCI is low, that means it is a excessive clogging, and if the intermediate value, for example, that HCR value is lies between 0.4 to 0.8, then you can say it is the equilibrium. So, for the assess of excessive geotextile clogging and soil retention criteria, so this is the very important test, that is a gradient ratio test and this long term hydraulic conductivity ratio or clogging test, because most of the cases when there will be the drainage and the filtration problem and there is a possibility for the clogging or the choking. So, how you can select the proper kind of the geotextile material, whether it is a open geotextile material, whether it is a non-open geotextile material. So, one must perform the gradient ratio test and as well as the HCR test, and then you can judge whether that material is suitable for that particular soil or not. If it satisfied this gradient ratio value as well as the hydraulic conductivity ratio value, then you can recommend it for this material. So, this is very important, because most of the structure that fail because for the clogging and because the choked. So, one has to be take care for the proper kind of the material, and they should select the proper kind of the geosynthetics material for the specific project. Proper selection of jute geotextile filter play significant role in making of the natural prefabricated vertical drain. The one hand, you know that that what is the natural geotextile material, and this natural geotextile material also can be made from the jute and the coir. So, this also very useful for the ground improvement, where we exclusively use the natural PVD material, and for this also you require the filter criteria. So, you require the three most important criteria: one, to ability to retain the soil, and then you require what is adequate permeability, and lastly you require resistance to clogging. So, these three criteria should satisfy. So, with this I end up this lecture. Please let us hear from you any question. Thanks for listening.